Let's demystify one of the most important equations in quantum mechanics, Schrödinger's equation. Schrödinger's equation describes how quantum systems evolve over time, revealing the wave-like nature of matter. Let's start with a time-dependent Schrödinger equation in its simplest form. This is Schrödinger's equation. It looks complex, but we'll break it down piece by piece. Let's understand what each part of this equation represents. Psi is the wave function. It contains all possible information about a quantum particle. I is the imaginary unit, and h bar is a fundamental constant of nature called the reduced Planck constant. H hat is the Hamiltonian operator, which represents the total energy of the system. Now let's understand what this equation actually tells us. The equation tells us how the wave function evolves and changes as time passes. The left side represents the rate of change of the wave function with respect to time. The right side shows how the energy of the system affects the wave function. This is what a wave function might look like, a wave spread out in space that changes over time. Let's use a simple analogy to understand this better. Think of the wave function like ripples on a pond. The equation tells us how these ripples spread and change over time. The wave function connects directly to probability. The square of the wave function's magnitude gives us the probability density of finding the particle at a location. Where the wave function is large, there's a high probability of finding the particle. Where it's small, the probability is low. Let's summarize the key insights from Schrödinger's equation. First, particles at the quantum scale don't act like tiny balls. They behave like waves. Second, quantum mechanics deals with probabilities, not certain outcomes. Third, the energy of the system determines exactly how the wave function changes over time. This equation explains why atoms have the structure they do and how chemical bonds form. The fuzzy electron clouds around atoms that you see in chemistry, those come directly from solving Schrödinger's equation. Why is this equation so important? Schrödinger's equation is the foundation of quantum mechanics and most of modern physics. It enables the technology we use every day, from computer chips to lasers to smartphones. It explains chemistry, helps us design new materials, and powers nanotechnology research.